Thanks very much, Joe, for the introduction, and thanks very much for the invitation to come and speak on home turf, as you say. So, first time in this building, but the surrounding areas are fairly well known to me, so it's nice to be here. Okay, so when speaking to Joe about the talk today, we had a discussion about the particular flavour that we want to bring to this, and one of the things that Joe said up front there is that for all the advances in different modalities and mechanisms of inhibition, there's an absolutely essential role for organic chemistry still in small molecule and arguably in large molecule drug discovery. So what I'm going to try and do today is fuse a talk around, I guess, fairly classical medchem programs with some insights around the organic chemistry, the synthesis that actually allowed us to move faster in these cases, actually, and that's something that I really wanted to pull out, that there's a continual focus and drive to just try and make programs be more efficient, faster, allow you to explore the SAR you really want in an efficient way. And here's one example that I can speak about now where we feel like we made some progress there. So I'm going to talk about two programs. The vast majority of the talk will be focused on our ERK1/2 inhibitor program. And I'm going to talk through really the hit to lead stage there. I'm not going to talk about the candidate. Unfortunately, this conference is 1 week too early to talk about the candidate. I'll be doing a first disclosure at the ACS next week on that candidate. So that's a bit unfortunate, but I'll take you up to where we got to with the lead molecule there. I'm going to talk about how some novel chemistry was developed to help us really progress this program, and that definitely bore out a faster candidate nomination because of it. And really the focus is going to be around how we've used chiral sulfamidates, and we've used them across multiple programs. We've done them in collaboration with some people like Adam. We've used them in the past, and actually our internal postdoc program was how we kind of really got this embedded internally. And I think one of the things I'd say up front actually that Adam mentioned was medicinal chemists' lack of variety and use of the chemistries that we apply. A slight tangent, one anecdotal tangent that I heard just last week is one of our lead synthetic chemists was doing an analysis of our internal ELN. And he asked me the question, how many of our overall reactions do you think are palladium cross-couplings? So I'll canvass the audience with how many reactions in an ELN or in a pharma you'd expect to be cross-coupling in the total number that we do. So more or less than 10%. More, right? Less than 30? More than 30? Craig's saying about 30. The answer was about 20, 25%. How many of those gives a product on the first attempt? Right, so this is an area that we all feel like we've advanced a huge amount in. Palladium cross-coupling, whether it be Suzuki or Buchwald couplings. Anyone want to hazard a guess how many of that 20% gives a product any yield in the first reaction? 20%. It's actually a bit higher than that. I think it's about 50%. But even still, I thought given that's an area that we all feel relatively comfortable in, it's still pretty low. So that's a slight tangent. So we're going to talk a bit more about chiral sulfamidate chemistry, and then I'm going to talk about one other program where we've used this chemistry to deliver a candidate as well. Okay, so really quick introduction to the biology of ERK. So ERK is an absolutely pivotal node on the RAS-MAP kinase pathway, so a really well studied and important pathway in a number of different oncology settings. So hopefully people are familiar with significant number of mutations in RAS that is prevalent in a number of different cancers, pancreatic, colorectal, and non-small cell. And obviously there's treatments out there for RAF mutation, and RAF mutation is present in a whole number of other disease indications in oncology as well. And ERK sits at the bottom of this pathway, and it's an absolutely pivotal node in this pathway. And it's responsible for a whole number of consequences at the bottom end of this pathway. So ERK's believed to interact with or activate about over 100 different substrates. So what's going on with the biology is hugely complex, but is it important? The answer is almost certainly yes. And we're seeing increasing numbers of candidates moving into development for the inhibition of ERK. And AstraZeneca are hoping to be there very soon. So a very brief introduction to the biology and focus a lot more on the medchem and the organic chemistry. So one slide summary of what we did to try and get a foothold in this program. So we ran a high throughput screen. What was really interesting there is that we didn't really identify any particularly novel or new scaffolds. So we parked that HDS relatively quickly alongside the high throughput screen. I guess AstraZeneca having a long history in kinase inhibition. One of the things that we'll do really early in a program is just mine the historical data for essentially activity against that particular target. So we did that, we actually found some hits. Those compounds, perhaps unsurprisingly, were very promiscuous against the kinome, and I'll show you some of that data in a second. And then the judgment becomes, well, do we think we can do anything to deal with that promiscuity and actually drive these towards selectivity? Clearly, I'm going to show you what we did there to try and move that forward. And that ultimately led to a reversible lead series, which I'll talk about more today. As an aside to the reversible series, we also found some pharmacophores that were very amenable to covalent inhibition. And we did a proof of principle there to actually look at covalent inhibition of ERK. We stopped that relatively quickly because we couldn't optimize that particular scaffold with a covalent warhead into good pharmacokinetic space. And there was also a question over whether or not you want a covalent 24/7 inhibition of ERK as a direct mechanism of action. We published that work in 2015, so I won't cover that at all today. So by promiscuous, this is what I mean, okay? So compound 1 is the hit that we found from our data mining and our looking across the kinase panels. This compound had modest IC50, about 40 nanomolar, and that's in an enzyme assay at the km for ATP, which is a pretty low challenge. It's about 60 micromolar in this case. And it did have some activity in our cellular setting, so against phosphoresc. So phosphoresc is one of the well understood downstream substrates of ERK, so that's a endpoint that I'll come back to as we go through the optimization. And then, it was reasonable molecular weight and at a relatively low log D, perhaps unsurprisingly given it was mildly basic. So the major challenge here, of course, is that in the limited panel of 128 kinases, we're hitting about 60% of them to greater than 80%, right? So there's a real challenge there. So what can we say about this compound and why did we think this might be a way to move forward? Well, obviously what we're able to do is find the binding mode for this compound in ERK. So it's an ATP competitive molecule that binds at the ATP site, displaces ATP. And if we zoom in a little bit on this structure, a couple of things to point out really. So the first thing is that the hinge interaction is in a classical sense from the pyrimidine nitrogen to the residue on leucine and from the donor to the carbonyl and this methionine at 108. The hydrogen bonds have disappeared for some reason. So that's fairly classical. The aryl ring and the base come out towards the solvent channel in, again, a fairly classical sense. And the reason for the lack of selectivity in this compound is that you're making a very strong set of interactions with this ASP167 and the conserved lysine 54 residue. So it's very unsurprising that compounds of this type and structural analogues of this type are unselective. So the challenge for us became very quickly is can we overturn that and can we get into a position where we think we've got reasonable equity that we can drive on the selectivity in the first instance, and obviously we were able to do that, or I wouldn't be telling you about it today. So what did we do first of all? Well, there was a few things that we did just to try and drive the selectivity in the first instance, and I'll talk you through those now. I think it's probably worth doing first of all those, because I reiterate a lot of this data throughout the talk, is just to walk through this table a little bit more detail so people are all on the same page. So what we have here is two different essentially ways of running the ERK enzyme assay, one at the km concentration for ATP and one at a higher ATP concentration as an increased challenge. That higher ATP concentration assay was run at more like 1 millimolar of ATP. So intracellular concentrations of ATP are variably described between 1 and 5 millimolar. So as you increase ATP concentration, you would expect a reduction in potency at the target, which is exactly what we see. I'll only really refer to the high ATP assay as we go forward, because you'll see that we end up getting to very extreme enzyme levels of potency that were below the levels of detection in the normal assay. The mode of action assay that we ran is essentially a multiplexed assay. This is in the A375 cell line, a non-small cell lung cancer line. And what we're able to look at in this assay, which is really cool, is you're able to look at both activation of ERK, so levels or inhibition of the phosphorylation of ERK by the upstream proteins. And then one of the immediate downstream substrates of ERK that I described was phosphoresc. So we're able to look at both of those in this assay. And what you'll see is that as we optimise our work in these compounds, you see variable levels of activity against both of these endpoints, which, if we're honest, is not something that was completely understandable as we went through this programme. But in some circumstances, essentially, we were both preventing the activation of ERK, i.e. having a good inhibition of the levels of phospho-ERK, and we were also inhibiting the downstream marker, phospho-RSC, which we would refer to as an inhibitor of catalysis. So you're preventing the downstream catalytic activity of ERK. So a couple of things we did first off, actually, is that one of the things that we did early on in the programme actually is remove this basic side chain. So these, although maybe not the whole reason for lack of selectivity in this programme, are relatively promiscuous in kinases. So by immediate truncation of this back to the THP, we were able to change the selectivity profile quite a bit in this series already. And that's without even thinking about whether or not we need to change interactions with the conserved salt bridge and lysine. And the reason this is likely to be happening in ERK is, I'll show you some structures later. There's a lysine that sits out in this pocket where we didn't always see it in the X-ray forms, but in some X-ray forms we did see a lysine, protonated lysine interaction with hydrogen bond acceptors in this region. And that gives you some level of selectivity for ERK. That's one thing that we did see. Not always present in the X-ray, as I say, but we believe that's partly the reason for selectivity here. And what you could see also here is we were able to start to drive forward the potency as well. So that lysine interaction, again, we infer was driving forward our binding potency. But the cellular mode of action assay perhaps isn't moving forward that much. The caveat, of course, being here is that when you're interpreting molecular mode of action assays and kinases, you really need to be thinking about it in the context of the selectivity of the agent in the first instance. Okay, so I think our view in the programme was that the potency against phospho-ERK and phospho-RSC in this original compound, we didn't feel comfortable you could attribute that to direct ERK activity, and more likely to be a combination of all the other kinases that you'd be interacting with. In this case, we're obviously improving the level of selectivity, so we're only hitting 14 kinases now, and we were starting to believe that we were maybe getting more modest activity against that's driven by ERK. As we moved on through the programme, we were able to cap on this nitrogen with this simple substrate. Again, you're really not driving forward cell potency. What we found was we started to drive lipophilicity in this region, and I'll show you why this is the case. You start to get really good levels of binding against the target. You're starting now to see what we believe is probably real ERK-driven mode of action activity, so 200 nanomolar as a preventer of activation and 80 nanomolar as an inhibitor of catalysis. Important to note that we've driven the lipophilicity up quite a lot from the start point here, so perhaps unsurprisingly you're really seeing problems with microsomal clearance in this case. So some progress, and obviously we've got the selectivity improved. We're now interrupting this salt bridge interaction. We're getting really better selectivity. You could start to try and temper the lipophilicity by hydroxylation on this side chain, and you were getting, again, here's one really nice example where we saw differences in profiles between two relatively similar compounds. Log D reduced, but again, clearance is still a problem. So why did this selectivity, why were we confident that we were changing the selectivity profile? So two things happened really when we got this X-ray structure. So this is the X-ray structure of the benzylated amide in green versus the start point in the grey colour. So two real things to note here. One is that you're seeing quite a shift in the position of that bicyclic system on benzylation. And what you're essentially seeing is, I didn't refer to this before, but this part of the protein here is what's referred to as the glycine-rich loop, which in ERK is relatively mobile. So what you're seeing is that this benzyl group is starting to really stick up into that glycine-rich loop, probably driving selectivity, and we feel it's probably stabilising some of the mobility in that glycine-rich loop as well, although that isn't proven. That is one of our hypotheses. The other big change we saw is the flipping of a tyrosine that's part of that loop from this position in the original structure right out of the way in the glycine-rich loop. And that's probably driven by the essentially binding of the benzyl group here. The other thing that's obviously changed a lot is this position of the ring. So you're no longer making any interaction to this ASP167, although you do retain an interaction with the lysine. So that's two reasons why we thought we were seeing some improvements in the selectivity in these molecules. And if we're honest, these things, based on our prior knowledge, were not that surprising, and obviously that's the reason that we picked a promiscuous compound, because we felt we knew there would be ways forward with that. Okay, so one of the other things that I didn't touch on in the original slide was that one thing that plagued the early stages of this programme actually was efflux in the compounds. So we did some things to try and look at that early on, and perhaps unsurprisingly, if we look at these two compounds here, we're now the methoxyethyl benzylic groups. We were able to get modest potency from these compounds in relatively good lipophilicity space, and generally their in vitro clearance started to come into a range that wouldn't be as terrifying as they were before. And you could see selectivity was being retained in these molecules. So one of the things we did early on was to try and understand whether or not this NH was a culprit in efflux. So when it's uncapped, you have an efflux ratio of about 10, so that's just simply the B to A ratio over the A to B ratio. Just for simplicity, I put all the numbers in here. One thing that's worth pointing out about most of these molecules is that their intrinsic permeabilities are actually really quite good. So the risk here is PGP substrate, and you're being pumped out. So what we were able to do here was we capped on this nitrogen. You can see immediately that we started to get essentially efflux removal, which was quite nice to see. The real issue we had with this series and these particular compounds is that methylation was a problem for potency, and we were never really able to square that completely, so I'll come on to show you how we dealt with that in the future. And then now I want to make that step aside into the synthesis part, okay, just to show you how we were making these compounds early on. I'm not intending going through these entire schemes. There's a couple of key messages that I just really want to land, but ultimately this group is the group that we were looking to vary quite a lot in the early SAR to drive the potency and the selectivity. And, you know, it's kind of MedChem 101. The things that you don't want to do is put the diversity step in first. And that's exactly what we were doing. Okay, so you're doing a Michael addition here to make this substrate, which you were then acylating, condensing to this substrate, making the 1,3-dicarbonyl, and then condensing it with another substrate here in the presence of ammonium acetate to get your bicyclic made. So, you know, chemistry that worked relatively well, but absolutely not a great place to be to drive your SAR in this region. You're then able to do a chemoselective methylation on this nitrogen, which is quite cool chemistry that was developed within the group. And then a pretty harsh, essentially, C2 chloro displacement with THP amine worked in reasonable yield. So this was obviously a problem as we were working in these molecules, and we wanted to think about how to overcome that. I'll come back to that in the future. The other thing that I don't have as much time to go into today, but a fundamental issue with these compounds that came out when we went from the in vitro setting to the in vivo setting is that these C2 THPs are really, really highly cleared in vivo, right? And actually, there's been work published externally on ERC actually with other groups that have found the same problem. So at the same time, we were finding that, you know, good potency and selectivity came from this THP, but the in vitro measure of clearance just did not predict the in vivo clearance very well at all. So on the x-axis here, we have the in vivo clearance predicted from rat hepatocytes. On the y-axis, we have the actual measured in vivo clearance and from rat cassette studies. And generally, you want to be within this kind of twofold ellipse for reasonable predictability, and you can see that where you have a THP, it's very rare actually that you're in a space that you'd feel comfortable you can predict. We made a whole set of different C2 groups where you're obviously trying to retain potency and selectivity. And the one that popped out really that others again have found independently was this N-methyl 2-pyrazole, which I'll come on and show you how that affected the properties of molecules in the future. So that's just segueing into where we went with our additional medchem. So if you'll then compare what that 2-pyrazole does in terms of the profile of the compound, you can see that you start to get essentially regression in potency, which was a real problem for us. So you can see that our cell activity dropped off. So we were taking a step back really to think about whether or not we can go forward in the pharmacokinetics, which is not uncommon. You could see that we did retain the selectivity, and actually what's quite interesting is this nitrogen acceptor almost certainly mimics this acceptor in terms of that interaction with the lysine in the active site. Problem here we had again was that as you were on this basic, this simple NH substrate, you were getting very high efflux. Capping of the methyl got you in a space that you would feel more comfortable in, but again, you still had that challenge. And I should say selectivity was still very good, and I've now introduced the rat hepatocyte clearance just to put that on scale, but you were seeing you're getting pretty good low turnover in human liver microsomes and in rat hepatocytes. but importantly, the way these converted to in vivo studies was more predictable from those rat hepatocytes. So potency was a real challenge then. So we then went back to the X-ray structure and we started to look in a relatively classical way about what type of chemistry we could apply or what types of substrates we could make to try and drive potency forward. And essentially we looked at, essentially we looked at a methyl scan on the substrate, on the compounds. So what you'll see here quite quickly is that we started to shuttle methyls onto the molecule in different positions. So from the structure, we felt that there was space in this region on this bicycle to introduce small substituents. This was, in the first instance, perhaps not that exciting at a cellular level. We just weren't driving against the cellular endpoint, which is a problem. What we found was, as we started to methylate on the C5 position of the kinase, which we felt would be tolerated, that sits along the hinge. That, again, is something from historical knowledge we know can drive potency. It can also often drive poorer selectivity, so that was a concern for us. In this case, we got a really nice result in doing that. We started to drive again on the cellular potency. So methylation in that C5 position, these two compounds are matched pairs. You are going from essentially no activity against phosphoresc to a couple hundred nanomolar, which was quite exciting for us. And the log D control was relatively good, around about log D of 2. We were getting, I guess, relatively high clearance in the human liver microsomes from this particular enantiomer. Rat hepatocytes was still in a reasonable range. So what was a really pleasant surprise for us actually, and you know, when we were doing the design, we didn't have a strong feeling as to which enantiomer might be preferential, other than that we felt they'd both be tolerated. We got a really, really nice bump in potency when we were at this particular down enantiomer in combination with the C5 methyl. So now you can see actually not only are we getting better activity against the phosphoresc endpoint, we're actually seeing that prevention of activation mechanism coming into play as well, which was really fascinating for us. And in general, the profile of this compound actually looked rather good actually. So aqueous solubility in a good place, log D in a good place, clearance, essentially no turnover in our vitro assays, and selectivity was in a good place. Efflux, not perfect, but given the really high intrinsic permeability of these compounds, we were comfortable in moving this compound forward as a way forward for us. So we were quite interested to try and rationalise why you might see such a big difference in that down enantiomer versus the up enantiomer in the side chain. And essentially what we could see from the X-ray structure, and this is where one of the points of contention is around what's actually happening here, is that the molecules you do see quite a contortion in how the bicyclic ring sits. So there's a reasonable amount of movement in how that bicycle sits, but you can see quite interestingly that these two methyl groups are quite well tolerated, and they're quite well tolerated in the sense that actually you don't see very much movement in these residues at all, and you don't see very much movement at all in the glycine-rich loop. So in this situation, it is not clear from the X-ray structure, at least just at the active site, as to why you see that massive hike in prevention of activation potency. As I say, the hypothesis that we have is that you are significantly stabilising that glycine-rich loop, but that's very difficult to tell just from these X-ray structures. That doesn't give you the whole story. So thinking about efflux and thinking about how to evolve the compounds further, we felt that probe molecule I showed you was in reasonable space. But what we wanted to do actually is just kind of ring the changes further to see if we could improve the overall profile, drive the potency further, etc. even more. And one thing that we do, and I guess is a fairly classic approach, is scaffold topping. So once you've got into a core, are you absolutely convinced that you've got the most optimal core, and are you happy that you're not missing something that's a relatively small chemical step away? So what we did here is we looked at a whole range of cores actually. I'm just going to focus on one, obviously one that moved us forward a little bit more, and that's essentially to try and remove this NH here that we felt might be implicated in permeability issues. If we move it to the internal bridgehead, you essentially replace it with a CH. And if you look at the quantum, the QM modelling of this, essentially the minima that's predicted is essentially the bioactive conformation that you would want to have, which is as drawn here. And what was interesting as well, and something that's really worth pointing out when you're thinking about these fairly classical kinase inhibitors, is that changes that you make at this C4 pyrimidine can often have significant or otherwise interactions with what's going on at the C2 group. So the overall balance of how your molecule actually sits in terms of its bioactive conformation can be changed in a subtle way that you maybe wouldn't predict in the first instance. So what we also looked at, of course, is what the effect would be from a computational and molecular modelling and actually quantum mechanics perspective, and whether or not there would be any interaction with either the THP or the pyrazole in this region. And we expected there wouldn't be, but additional substitution here almost certainly would, so we steered away from those in our design. And again, just going to the chemistry then, so this was a new sub-series essentially that we were wanting to make now, so we were still essentially labouring a pretty old school route, if you like. So we would access stocks of this material. You could regioselectively cross-couple to the C4 position to get to this position here. You could debulk. You could then do essentially an alkylation with a very reactive chloroacetone. Then you were introducing that diversity again relatively early. And then this reaction here, this trimethylaluminium reaction to snap shut the ring was fairly capricious, and as people have done this know, it's a fairly messy reaction. And then to introduce the pyrazole, we were now using variations on different types of Buchwald cross-couplings, which were reasonable yielding, but again, not probably the most elegant route. So we kind of took a step aside here and thought, okay, so what we want to be able to do is think, more closely about how we're going to introduce this centre, but also whether or not there's ways to introduce this diversity later in the synthesis. And one of the things that we focused on was the use of these chiral sulfamidates. So chiral sulfamidates, in their most general sense, represented by this type of core here, introduced in 1990 by the Baldwin group. And what's really nice about the sulfamidates is it gives you that C2 linker that classically you would think would come from an aziridine. And aziridine chemistry obviously is fraught with a number of issues. Even just getting hold of the reagents is a problem. Their polymerization can be a problem. And the breadth of scope and stability of those reagents just they don't attract you to something that you want to rush into in a kind of lead optimization phase. So we thought quite a lot about these sulfamidates as a way forward. And for those that are not familiar with them, they're really nice molecules to handle and use. And the way they're made is usually from chiral pool starting materials, where you can have a variable length of linker, n equals 0, essentially comes from amino acid derived reagents. N equals 0, n equals 1, you again can get some chiral pool sources. Phenyl chloride in the presence of base gives you the intermediate here, and then a simple sodium periodate ruthenium chloride oxidation gives you the sulfamidate. And R1 is often Bock or benzyl, relatively amenable groups to remove later on in your synthesis. And in our experience, most of the time these compounds are stable, air stable. You can store them, you can keep them on the bench, and of course they become a really nice source of reagent for broader use within the group. Whereas storing chiral aziridines is just not really something that you would want to consider. And then more recently, there's been some nice work where you can essentially make these directly on more complex substrates through sort of CH activation chemistry, which allows you to make some substrates that maybe wouldn't be amenable to the more conventional oxidative conditions here. So the field is kind of emerging in the utility of these compounds. And I just want to give you a little bit of context about how these have that kind of message that Adam was getting across about how quickly or how long it takes for chemistry to permeate into organisations. And the analysis we did was we looked at our ELN from 2007, so that's when AZ introduced essentially a searchable ELN, and since then there's been over 750, it's probably more like 1,000 now, actually this slide's a little bit out of date, examples of that sulfamidate ring opening chemistry in our chemistry, okay? Now, that may only represent 4 or 5 projects, because obviously we're doing a lot of chemistry in any given programme, but I think it gives you a flavour for how many times we've been doing this. And the kind of work that we use, the kind of chemistry we've done on these is perhaps unsurprisingly both amine and alcohol ring opening to give you, what look like really useful medchem building blocks. Some really nice chemistry's been done around C3 activation of indols. And some really nice work's been done around essentially making functionalised Greenyard reagents, which again can ring open these systems very, very elegantly. This work was essentially the main focus of a postdoc that we had within the group, a guy called Tom Moss. And we got into this area around that whole notion of moving away from flatland, so the kind of the 2009 paper. So we were thinking about, what does that really mean to us? And we were really starting to think about the utility, and it actually comes to bear in ERC, actually, this programme, is the utility and the availability of semi-saturated bicyclic systems. So that's how we get into this. You can imagine the work that Tom developed was to further essentially functionalise here and then ring close back onto this system to get a really elegant way, fast way into chirally pure semi-saturated bicycles that we thought would be of high medchem relevance. So the particular piece of work that was of more relevance to ERC was that we were actually shown as well that you could open these ring systems really nicely with both monocyclic and bicyclic heterocycles, and you can see again the kind of substrate you make there, and then obviously you can do other types of kind of functionalized metal reagents to ring open these. So just to give you a small flavour of the kind of work that we were able to do really quite quickly here, we were able to stockpile this reagent, which wasn't difficult to come by, as I showed earlier, and then under relatively mild conditions, potassium carbonate 18 crown 6 and dioxane at 50 degrees, you're able to spring that ring open, and in all the cases essentially we were able to access these substrates from that two-step process that I showed, and generally the reagents were stable. In some cases you leave the Bock group on, so I've just showed the isolated yield for the Bock protected material, because in some cases where you take the Bock off in situ you get cyclization. In these cases you don't get that, presumably because of either the reduced nucleophilicity of this nitrogen, so you're able to deblock these and have it as a stable intermediate. And we were also able to actually show, of course this is not as selective in terms of the chiral transfer, but you can actually get secondary alcohol to work quite well here as well. And in this case with the dimethylamine, we again were able to deprotect and it wouldn't cyclize. And in general the yields are 50% plus, and this is obviously the two-step process to get to here, but often in the high 90% yield for those reactions. So this really was a fundamentally useful process for us that we used a lot. Now, I guess the message here is that the compounds that we ended up selecting were relatively conservative in what we had. What we had in the functionalized position, if you like. That's not to say that we didn't go a lot more elaborate and a lot more extreme here, if you like, in terms of optimizing the chemistry. The reality is the best compounds came from the simple methyl, but the message is we probably, I don't know how many we made in total, but it was probably 20, 30, 40 different combinations of chiral substituents made on those rings. And I would really defy anyone else to go back and do that by the method we were using before. So whereas this chemistry looks on paper really simple, it actually had a massive influence on our ability to move forward here. So what I wanted to do now is just quickly show you what some of the better compounds or the lead compounds look like when we made this bridgehead compound. Keep on flicking the next one. So here's a compound that we were able to get to relatively quickly, and you can notice that we kind of really started to re-optimize on the benzylic position here to an aryl group that's of relatively low lipophilicity, and this worked out quite well for us. You'll notice here again that we lost that prevention of activation mechanism, so it really was a case of that being an empirical observation that we never quite understood fully how to optimize in. What you can see with these compounds again is we were getting reasonable stability in cellular in the in vitro systems, and you can see actually the permeability in general was still bobbing around what we ended up with the N-methyl versions of the indole. So the reality is we were never able to get these compounds into extremely low efflux positions. But what I have put in here is just to give you that feel for the intrinsic permeability of these molecules versus the reflux, because that's a really important message. So the way the intrinsic assays run is usually in the presence of PGP inhibitors, so you're literally just looking at the cell permeability across the membrane. And where you have real issues, obviously, whereas that intrinsic permeability is very low and you have high efflux, right? That's a problem situation. In this case, we are clearly PGP substrates, but the A to B intrinsic permeability is extremely high. So then it just becomes a risk discussion about, do we think we'll get enough dose on board when we have that level of efflux? And in this case, we felt we could move forward on that basis. So what we did next, again, was from this new core, if you like, we then started to introduce the chirality, and the C5 methyl again was already introduced here. And what we came out with, same as we saw with the NH pyrrole here, is this down methyl was much more preferable. The C5 was very preferable. You can see the levels of cellular mechanism of action potency we got now. Again, that prevention of activation came back in really strongly, and the downstream inhibition was also pretty strong. Good solubility. I'll come and show you this in a minute, but we actually, because this was a lead compound, we went in at a larger kinase panel, and we saw, again, a really nice selectivity profile. In vitro clearance, very little turnover in these molecules. Again, really nice place to be. And you can see actually the best compound of this set, extremely good intrinsic permeability with a modest efflux, certainly not no efflux, but manageable. So this is how it actually played out for us in terms of the chemistry. So I'll just essentially skip straight to the key step, really, the pot carb driven ring opener of the sulfamidate. In this case, it's very high yielding. You were able to take off the bot group, and then under basic methanol conditions, you can get cyclization to this product. And then what was really cool, actually, and this is how we did most of our optimization, is once you had made this core, we were able to get a selective N-alkylation of various different functionalities here. So now you're introducing your variability in the second to last step, which is a much better place to be. And then, again, the Buchwald catalysis to put in the pyrazole. And this is essentially where we got to with this particular lead identification. So this is the molecule that took us from the hits to lead into the lead op stage. Okay, so that's the quality of the molecule that we got to. You can see it's absolutely unquestionable we made a huge difference to the selectivity in this molecule. What's really interesting, and again a kind of point of caution or note of caution, is that we were inhibiting about 9 kinases at greater than 80%, but if you actually look into the detail of those kinases, all the ones that have got an asterisk here, these are actually assays in the Thermo Fisher panel that couple through ERK. So we do not believe that the compound is actually active at RAF or MEK. In fact, we know it's not active at MEK because we had an additional assay we could look at there and show that compounds are not MEK inhibitors. So this was a really nice molecule for us to move into the lead op stage with. And just to give you a little bit more information on the profiling of this compound, obviously we wanted to take this compound in vivo, so we had to understand how well it was likely to perform in vivo. So in the left-hand panel you have a classical plot of the fold-free cover in plasma over the cellular endpoint, the phosphorisk endpoint. And you can see you're getting essentially 24-hour coverage at 100 mg per kg daily dose of this molecule, so a very good exposure for a probe. And a bit more detailed pharmacokinetic profiling of this molecule, so the free levels of the molecule are pretty good. Clearance in rat is actually about 50% liver blood flow, so it's fairly high still, if we're honest. Dog, again, 50% or so liver blood flow clearance, but getting good bioavailability in dog, modest bioavailability in rodent. No turnover in human hepatocytes, so very low turnover in human metabolite. And then a really simple dose prediction here based on some of the PD data I'll show you, and looking at the variability and potentially putting the risk factors in around clearance. You predict a dose less than 250 milligrams from this compound on a once daily basis. But as I say, this isn't the candidate. This was a shortlist molecule that we took forward. So this molecule on the left-hand panel showed some quite nice efficacy in a non-small cell lung cancer model. In this case, the CALU6 model. So 50 mg per kilogram, you're getting regression of the tumour. 15 mg per kilogram, you're getting essentially a tumour stasis. And at a lower dose of 5 mg per kg, you really don't see an effect. And here's just a couple of PD endpoints that we looked at. So phosphor-Fra1 is one downstream marker, and phosphor-Risk is the one that we focus more on. At that higher dose, you were getting essentially greater than 70% inhibition of that marker at 6 hours post-dosing. So you were hitting the marker. We felt we could probably do a bit better than that actually with other compounds. So that was one of the things that that pushed us to go even further than this molecule and try and drive down on the potency and the lower the predicted human dose even further. So that's essentially where we got to. We got to that really quite nice probe molecule through that combination of understanding the selectivity issues, dealing with those selectivity issues, and then using fairly classical kinase med chem to drive forward both the potency and the selectivity to get to a probe molecule. And obviously applying that sulfamidate chemistry did shorten that time from finding that lead to actually selecting the molecule. The second project that's just really quickly going to highlight in the last 5 to 10 minutes is our interest in the selective estrogen receptor degraders. Okay, so AstraZeneca has got a very long history in this area. So the marketed drug fulvestrant, which is an antagonist and a degrader of the estrogen receptor, is this steroid-derived agent. And that was developed and is used to treat locally advanced and metastatic ER-positive breast cancers. So a really, really powerful agent in that setting. The major downside of fulvestrant, if anyone knows this area, is that it's given by monthly intramuscular injection in the buttock. So, and we think that the efficacy is limited by how much you can actually inject. So there is an opportunity there with a more advanced and oral agent. You could push on target even harder. So AZ for a number of years has been interested in this field to try and find oral inhibitors or oral degraders of the estrogen receptor. And I'm doing a disservice to the guys that developed this work, but a number of years ago we put this compound into clinical trials, which is known as AZD9496. And this is a selective oral estrogen receptor degrader, and that work was published by DeSavi et al. in 2015. So what's interesting about this molecule, of course, is it's got a really interesting chemistry, right? So it's based on this tricyclic indole core. And the way the guys were making this core and the way we make this internally is you do an alkylation on the nitrogen. So again, you can start to see where we might be going with this, but you've got the chiral ethyl group here. You can alkylate here. You can then do a Pictet-Spengler cyclization to get the diastereoselective product here. And then through saponification, you're able to get to molecules of this type. Now, the team obviously here were in a position where they really need to think about how they're going to functionalise the med chem on these targets as well. And you can obviously think that the complexity is probably even greater than what we saw in the ERC project. So again, in this situation, the way the guys were originally thinking about doing this is, chiral pool to find a number of different tryptamines and derivatives thereof. Functionalization of this system from different types of chemistry onto aldehydes here, and then obviously reductive amination on different types of ketones here might allow you to get into different chiralities there. And that's what we were doing in the first instance. But the chemistry that was developed here was really neat, actually, and you were able to get that C3 selective ring opening of the sulfamidates. And the guys were able to therefore use really readily available and simple to access indoles as they're functionalizing left-hand side of the molecule. And they were able to spring open a whole range of sulfamidates to allow them to both vary this region and obviously the R2 region. Some of those examples are just shown here. And that, again, to us just showed you the power and utility of that piece of chemistry, allow you to access a number of different cores. And that's ultimately was very successful and has been used since in the project to further develop the SAR in that series. So hopefully that's been a bit of a whistle-stop tour of both our med chem but also where synthesis can really impact on the progression and speed. And actually the fundamental thing here is, are you asking the SAR questions you really want to ask, or is chemistry limiting? And I think that's what this story for me is all about. So although we ended up with the chiral methyls in both cases, we absolutely didn't stop there. That wasn't the limit of where chemistry could take us. We did a whole lot beyond that. We just never found a compound that was more optimal. But you absolutely want to be in that position rather than only being able to make the one or two substrates and not be able to fully interrogate your SAR. So hopefully I was able to show you we were able to come up with pretty high quality ERC leads, although we didn't and we still don't fully understand all of the cellular mode mechanism of action SAR. And we do have a clinical candidate from this work that we will disclose in due course, and it is also heavily relying on that sulfamidate chemistry. X-ray and conformational analysis was really important for both driving the selectivity but also the scaffold hopping, and we think that was very useful. And the sulfamidates obviously have been something that really have driven forward 2 programs that we've selected clinical candidates from now. So on that note, I will thank the global teams, far too many to list here. Special thanks to the 3 Toms listed. Tom Hunt, Tom Moss and Tom Maguire. It's a really good precursor to getting a job at AstraZeneca these days to be called Tom. So Tom Moss was really instrumental in his postdoc in actually bringing that sulfamidate chemistry into AZ. Tom Hunt and Tom Maguire have taken some of their slides, quite frankly, so that's where there's plenty of thanks. Scott Lamont, Jamie, Richard, these guys are all massive scientific contributions to a lot of the stuff that I presented there. And thank you for your attention. I think I'm on time, so take some questions. Thanks.